So you have this object and you throw it at a speed of, let's say you give it an initial speed of, let's say 8 meters per second. And of course, we'll also need to know information about, for instance, the mass of the object and the height of the building. So let's say the object has mass 5 kilograms. And let's say its starting height is 20 meters. And we could use standard conservation of energy to address questions like how fast is it going when it hits the ground, or how high does it get at its maximum height? But that only looks at specific instants in time, and we have to rerun the calculations for every one of those instants. If we want to look at more of a big picture, broad idea of everything going on during its flight, it's often a good idea to graph the energies so we can look at not only specific instants, but the entire span of time that it's happening. So if we make a graph of distance versus energy, and in this case, the distance we care about is height, because we're talking about how high it is off the ground. So this axis we're going to label y, the height, presumably as measured from ground level. Doesn't have to be measured from ground level, but that's probably going to be most convenient. And then this axis would be energy. And I'm not going to label it with a specific type of energy because we want to be graphing potential energy of gravity. And also, what else do we want to graph?
Kinetic.
Right. This object is in motion, so kinetic energy is going to be important. So one thing we can do here is, if we want to be really precise about the graph, we can set up a data table. We want to compare height, potential energy of gravity, and kinetic energy. And also it's a good idea to work with E total as well, and a variety of different heights. What are some important heights we should be considering here?
The initial height?
Yeah, the initial height, 20 meters up. So we definitely want to consider y equals 20. I'm going to put that in the middle because we might need some heights above and some heights below. What other height is probably going to be important here?
0, like on the ground?
The lowest you can get in this situation is 0, assuming that it can't go through the ground. Then we have to stop the simulation at 0. And we might want to try an in-between point. Let's just say we throw in 10. Could also try maybe 5 and 15 if we need more information. And let's try maybe 30 also. And see what happens. We can calculate the potential energy for each one of these, because what formula can we use for potential energy here?
Mass times the gravitational constant, or I guess acceleration.
Yeah, that is acceleration of gravity near Earth's surface. Yeah, times the height. And we use just y instead of delta y, because in this context, we're not looking at how much the gravitational potential energy is changing. We're looking at how much there actually is at each one of these locations. And m times g, we have m, that's 5, and gravity we're rounding off to 10, so this just becomes 50 times y. Which means all we need to do is multiply each one of these heights by 50. 0 times 50 is 0, 10 times 50 is 500, 20 times 50 is 1,000, 30 times 50 is 1,500. So we've got all these values for potential energy. And we could plot those on the graph. If we just mark off maybe 5, 10, 15, 20, 25, 30. And let's just mark these off in 500s. Something like that. So we can plot these points, 0, 0, 10, 500, 20, 1000, 30, 1500. And what shape are these forming if we were to connect these?
Line.
Yeah, and we should expect this to be linear because we have the function that says output equals a constant times input. Anytime you've got output equals a constant times input, that's always going to be a straight line, and moreover, it's going to pass through the origin. So here's our potential energy of gravity graph. Mathematically, it just keeps going as a line forever in both directions. Of course, in practice, we wouldn't extend this one beyond 0 because we're treating 0 as ground level. And it's not really going to go up forever either because the ball doesn't keep going forever. But mathematically, the function output equals 50 times input is going to be a straight line with slope 50. So there's our potential energy graph. Any questions on that so far? And is there any kinetic energy we can calculate?
We can know from the potential energy that the max value is going to be 1500, which will be the E total.
Why 1500?
Because that's the highest value of potential energy of gravity.
That is the highest value we calculated.
Yeah.
But that's just because I happen to write a 30 here. Could we plug in a higher number? Like, could we plug in 40 for height?
Yeah.
Yeah.
Wait, we also have initial velocity or speed, right? So then our
Mhm.
so we would our like total would be PE plus KE.
Yeah, we could actually make use of that because from the potential energy graph alone, we can't really do anything else. But we do have one single piece of information about kinetic energy. We know the speed that it starts at. So we can calculate that kinetic energy at least using our usual formula, 1/2 of m times speed squared, mv squared over 2. So we plug in the mass. The speed squared is going to be 64 divided by 2. So we get 32 times 5 would be 150, 160. Does that work? Yeah, so that means that the kinetic energy at that instant is 160. And specifically, where should I fill in that 160 on this graph?
At where the potential energy is 0.
At
Where the
20.
potential energy is 0? Is that where we threw?
Oh, no, at 20.
Right, because the important thing is we threw the ball at this speed when it was 20 meters high. So the 20-meter location is the location where we threw the ball from. That's where we gave it the 160 joules of kinetic energy. So we know at the location it was thrown from, at the very beginning, we know the potential energy is 1000 because we can calculate that from the height. And we know the kinetic energy is 160 because we can calculate that from the speed. So we're providing a starting location and a starting speed. The starting location tells us the potential energy. The starting speed tells us the kinetic energy. We don't yet know the kinetic energy anywhere, anywhere else because we don't know the speed anywhere else yet. We don't know how fast it's going at this location or even when it hits the ground. So we can't fill those in yet. But most importantly, if there's one single location where you know the potential energy and the kinetic energy, and we can fill that in on the graph too, by the way. We know at 20 meters, we got 160 joules of kinetic energy. That's going to be something like this. So we have 1 point on the kinetic energy graph. If you know both of those values, what can you now calculate?
The E total, but I have a question.
Mhm.
So since like the height of 30 is non-existent in this scenario, since the highest that it goes is 20, and it's like not saying that it's thrown up and then down.
Well, in this case, we are throwing it upwards.
Because then you can't have negative kinetic energy.
Right.
So the E total wouldn't be the same.
Well, let's try it. We can find E total by just adding these together. So at location y equals 20, we add potential energy plus kinetic energy, 1000 plus 160. So we know that the total energy at that location is 1160 joules. And if we're assuming that this is a closed system, what does that tell us?
But it's constant.
Right, constant total energy. We should expect the total energy, if it's this value here, then the total energy is that same value everywhere. What would that look like on the graph?
It would be a straight line at the top at,
Mhm.
or not at the top, at 1160.
Yeah, at 1160, we're going to have, and I would say not only a straight line, but a horizontal line, because it is a constant value. If you're graphing a value that's the same everywhere, that's just going to be a horizontal line on the graph. So 1160, something like that. So this horizontal line represents E total. That's the value of E total everywhere. And now that we have that, we can also calculate what else?
The kinetic energy.
Right, because kinetic energy in this case is just going to be the difference between potential energy and E total. Since the total energy is potential energy plus kinetic energy. And I want to emphasize this next step only really applies if there's only two types of energy changing. Because if you solve for kinetic energy, you just get E total minus potential energy. If there were other types of energy involved as well, then this would be more complicated. You'd have E total minus potential energy of gravity, maybe minus some other things as well. But in this case, we just have two things that add up to a constant. Since we know the total energy everywhere, and we know the potential energy everywhere, we can calculate the kinetic energy everywhere as well by just subtracting. E total minus potential energy, 1160 minus 0, 1160. So we can plot that on the graph. When y is 0, kinetic energy is 1160. And by the way, what could you then calculate? If you know the kinetic energy, you can sort of reverse the usual formula and solve for what? What's the indicator for kinetic energy?
Oh, velocity.
Right. So now that we know the kinetic energy at the instant it hits the ground, at the instant it reaches y equals 0, we could set 1160 equal to 1/2 mv squared and solve for speed. Figure out what speed it's going at the instant it impacts the ground. So this is one possible use of this analysis. We can figure out how fast it's going at the instant it impacts the ground. Or anywhere else. Like for instance, at height 10, what would the kinetic energy have to be?
660.
Right, subtract those, 1160 minus 500, we get 660. And you could solve for the speed there as well. Set 660 equal to 1/2 mv squared, solve for v, and that tells you how fast the ball is moving as it passes by the 10-meter mark. And we could graph that as well. 10, 660, something like that. I think that's about right. Yeah. And what about at 30? If we got potential energy 1500, total energy 1160, what would the kinetic energy be there?
Negative 340,
Yeah. And why is that a problem?
because kinetic energy can't be negative.
Right. Kinetic energy cannot be negative. Mathematically, there's nothing wrong with this graph. You just have this line going from here to here. But since kinetic energy cannot be negative, because m is always positive, and speed squared will always be positive, that means this does not happen. What does that tell you about the actual physical behavior of the ball here?
It's not going to achieve a distance greater than 20, at least not as far as 30.
Yeah, although I wouldn't necessarily say it can't get higher than 20. We're starting at 20 and we are throwing it upwards, so it is going to go up. But I would say it's not going to be able to get all the way up to 30. So 30 is definitely unachievable. The ball does not have enough energy to get to 30. It could if we add more energy. If we threw it at a higher speed to begin with, then it would have more total energy. And it might, as long as the total energy was 1500 or more, then it would reach 30 meters of height. But since it doesn't have enough energy to do that, that's not going to happen. So we know it doesn't get to 30. We know this point shouldn't actually be included on the graph. But we could figure out how high it goes by looking for an intercept. It looks like these kinetic energy points, what sort of shape would you expect those to form on the graph?
It would be a linear line, but then it would form a triangle.
Yeah, it looks like this is also going to be linear. And why is that? Why would we get a linear function for a kinetic energy graph? How are we calculating all these kinetic energies in the first place?
Just doing E total minus the potential energy.
Right. E total minus potential energy. And since total energy is constant, that means any change in potential energy is matched by the exact opposite change in kinetic energy. Potential energy increasing at a constant rate means kinetic energy decreasing at the same constant rate. So whatever the slope of potential energy is, kinetic energy is going to have the exact opposite slope. Also, we can see this with more of the theory of graphing. If we reverse the order on this, I find it useful to write kinetic energy here as negative potential energy plus E total. And potential energy is just this MGY formula. If we fill in potential energy with MGY, what shape do you get if you graph just MGY?
Line.
Yeah, MGY is this line we already graphed. And in terms of the algebra of graphing, what happens to a graph if you take a function and apply a negative sign?
It slopes downwards.
Yeah, or I would say, since it's already sloping upwards, it's going to slope downwards. But more generally, what happens to a graph if you apply a negative sign? Like, let's say you have some weird shaped function and you apply a negative sign to it. What happens to the graph?
Oh, it flips.
Yeah, it's just going to flip across the axis. So this graph, we've got this graph of potential energy, just shaped like this straight line. All this negative sign is going to do is flip it across the axis. So negative potential energy looks like this shape. But then we're also adding E total. And E total is a constant. What does plus a constant do to a graph?
It just moves the y intercept.
Yeah, all that does is just shift the graph. Not just the intercept, but the whole graph shifts in that direction. So if we're just applying a negative sign, the negative sign takes the graph and flips it across the axis. But plus 1,160 takes that and shifts it up 1,160. So that's our kinetic energy graph. And again, this only works because we just have two types of energy that add up to a constant. But that always guarantees that the missing type of energy is just the type of energy we already know, in this case, PE gravity, flipped across the axis and shifted by an amount equal to E total. So that gives us our kinetic energy graph. We know this is going to be linear. So we should be able to connect those, straight line. And we can see from the graph, it looks like this is going to hit 0 somewhere around maybe 24-ish. And note that that's at the same Y value, the same location where potential energy intersects E total. Because if potential energy is equal to E total, you've got 1160 minus 1160 is 0. So you can always find a location with no kinetic energy by looking for a location where potential energy intersects E total. And again, this only works because we have only those two types of energy changing. If there were more types of energy involved, it would be more complicated.
So if there are more types
Sorry, what was that?
types of energy, do you have to just individually calculate every point?
If you have more types of energy, you said?
Yeah.
Yeah, in that case, I would, and again, it's a good idea to set up a data table like this. You'd have maybe potential energy of gravity and potential energy of spring and kinetic energy and E total. And in that case, yeah, you want to look for maybe a location where potential energy of gravity plus potential energy of the spring equals E total. That would be where kinetic energy is 0. Alternatively, another way you could do that is to just make one column for all the types of potential energy added together and another column for kinetic energy. So in that case, instead of graphing potential energy of gravity and potential energy of spring separately, you might just make one graph that represents all the forms of potential energy added together and another graph on the same axes that represents kinetic energy. So sometimes that's an easier way to see where one of them is going to be 0.
Sorry, would you recommend going about problems like this in this way even for the exam, or do you think it would be too time consuming?
I mean, some part of the problem of this, of course, is that it takes a long time. So I would certainly recommend going through all the steps at least a few times when you're practicing it in the first place, just to get some experience with how this all fits together. But in practice of actual problem solving on a time limited situation, you don't want to go through all these steps, of course. So what I would recommend in that case is try a faster sketch. And maybe instead of writing out the entire data table, you might take a look at the fact that potential energy here is mg, which is 50 times y. Take a look at this equation and notice that, oh, this is going to be a slope of 50 straight line. And then maybe just calculate 2 points on the line, because 2 points is all you need to draw a complete straight line. And then instead of calculating, and you certainly want to find a value for total energy, so you can get the value of total energy everywhere. But then for kinetic energy, instead of making all these calculations, you could notice that the kinetic energy is just negative potential energy plus E total. So that's going to be potential energy graph flipped across the axis because of the negative and shifted because of the plus E total. So you want to get into the habit of quickly sketching these graphs as well as being able to work it out more precisely from the calculated values. Both of them are useful skills to have.
Okay, thank you.
Mm-hmm. And also an important thing to look for when you're doing a quick sketch, if you want to know a location where kinetic energy is 0, again, assuming there's only 2 types of energy involved, if you want to know a location where kinetic energy is 0, look for a location where the potential energy graph crosses the E total graph. Because if potential energy equals E total at that point, then there's nothing left over for kinetic energy. And that's very useful because that tells you a location where the object or objects come to a stop and presumably turn around. This location looks like maybe 24 or 25 meters is where the object stops going up and starts falling down. So that would be the maximum height we're looking for. And again, we can tell from the graph that looks like it's about 24 or 25 meters. We can calculate that more precisely though by saying, let's say y is unknown. And we want to know at what location does the kinetic energy reach what value? What's the value of kinetic energy when the object reaches its highest possible location?
0.
Right. If it's at its highest location, that means it has come to a stop. It's stopped moving up. It's about to start moving down. So kinetic energy at that highest location, let's say y max, which we don't know yet. We know at that location, the kinetic energy has to be 0, which means what's the potential energy?
1,160.
Right. Potential energy has to equal E total. And this is just the numerical equivalent of looking for a location where the potential energy matches E total, because then kinetic energy would be 0. So now that we know the potential energy of gravity at that location, how would we find Y max? If you know the potential energy, how would you find the height?
You'd set 50y equal to 1,160.
Yeah, because we already know potential energy of gravity is given by 50 times y in this case, mass times gravity times y. So we can say 50y equals 1,160. And then we can solve for y just by dividing both sides by 50. Looks like the times 10s cancel out. And that's 23 and a fifth. So there's the y max. And note that our original graph here got us a pretty close estimate in the first place. We were guessing about 24 or 25. Looks like the actual value is 23.2. So that's the actual maximum height. The ball reaches a height of 23.2 meters. That is 3.2 meters above where we threw it from, and then falls. So the actual trajectory of the ball, it starts at 20, it goes up to 23.2, getting slower and slower, and then it starts to fall, getting to lower and lower y values while getting faster and faster, kinetic energy increasing. Any questions on that so far?
Yeah, I have kind of a conceptual question, which is kind of related to this. Let's say they gave you the graph, or they didn't give you the graph, they gave you the table here with all the values, and they said that instead of throwing the ball up, you'd throw it down at the same speed, and you're also ignoring friction and all those other forces. So it would be going the exact same speeds no matter what, right?
Yeah, because notice that this graph doesn't really describe direction at all. This graph is saying when the ball is at 15 meters, it's going to have this much kinetic energy. That's true whether it's 15 meters on its way up or 15 meters on its way down. And also, when we were calculating the initial kinetic energy in the first place, we didn't really care which direction it was traveling. 8 meters per second squared is 64. Negative 8 meters per second squared would also be 64. So the direction of travel doesn't really influence the values on this graph. If we threw it down, we would probably ignore everything past 20 because it's not going to be going up to those locations. But everything less than 20 would be the exact same graph. To put it another way, if you throw a ball up at 8 meters per second, and I watch as it goes up and starts to fall back down, and the instant it passes me, I throw an identical ball down at 8 meters per second, they're going to be traveling exactly together with each other from that point onwards.
I see. And then if let's say you're ignoring air friction and it also bounces perfectly, like all the energy when it hits the ground doesn't go into the floor, it goes back into the ball, it would bounce all the way back up to the max height of 22.2.
Yeah, if we assume a perfectly ideal bounce with no energy loss, it hits the ground with some very fast speed, whatever we calculate from the final kinetic energy. Hits the ground with some fast speed. If we assume no energy loss during the bounce, it's going to rebound with that same speed on the way up. And with that same speed, it's just going to repeat this process identically. It's going to be moving upwards, losing kinetic energy, gaining potential energy until it comes to a stop at 23.2. Then it's going to fall back down, gaining kinetic energy as it loses potential energy, hits the ground, bounces, and goes back up. And this is assuming if there's no loss in energy with each bounce. Realistically, each time you bounce, hitting the ground and rebounding involves losing some energy. Some of the kinetic energy turns into thermal energy instead. So the ball is going to bounce less and less and less. In fact, ultimately what's going to happen is each bounce is still going to have a kinetic energy graph that's a straight line, but a little bit lower. With each bounce, you're lowering the total energy a little bit more because you're losing some energy with the impact. Of course, that wouldn't be a closed system, so this model doesn't really apply as well. But the concept is still the same. You're just losing energy with each bounce.
Got it. Thank you.
Any other questions on that? All right, let's try out this one with the rocket and chemicals and conservation of energy. This is the practice quiz 3.2 that was linked in the chat. Let me pull that up on share screen for a moment. This one here. So we've got a toy rocket. We know its mass is 4 kilograms. We want it to get to 30 meters high. We know how much fuel it has and how much oxygen it has. And when it reaches 30 meters, half the fuel is consumed. We also know it's getting force from air resistance and it's losing some heat. We also know chemical X is delta H, how much energy it produces per mole. And we're assuming that the resulting exhaust and the water all fall to the ground afterwards. And what are we actually trying to find here? Looks like we want to know the speed, right? So let's start by drawing out initial and final situations. If we have our initials, what would we use as initial and final situations here? Is there some location or some instant in time where we know everything, or some instant in time where we're trying to find something?
The Y initial would be 0, since we're launching from ground level.
Yeah, if we start off at that instant of launch, we know lots of stuff about that instant. We know where it is, we know it's not moving yet, and we know how much fuel it has. So the initial is at ground level, full of fuel, at rest. It is ready to launch. And what would we use as final?
The height of 30 meters.
Yeah, once it reaches 30 meters. So final is going to be rocket, and I think also half the fuel, because it says we've burned half the fuel, but the other half is still in the rocket. So we're going to have to treat the other half of the fuel as being still in the rocket. And it's in motion with some unknown final speed, with half the fuel consumed. And also we're assuming all of the resulting exhaust has just fallen to the ground and at rest. So we can treat that as essentially not even part of the system anymore. So with this, from this initial to this final, what types of energy are changing? What would we have to include in our equation?
You need to include the gravitational potential energy,
It is changing height, so we definitely include gravitational potential energy. Increasing or decreasing?
it would be increasing.
Yeah, we've gone to a higher height. In fact, we even know Y initial and Y final. What else is changing here?
The kinetic energy.
Yeah, kinetic energy. It starts at rest and now it's going faster. So the kinetic energy has increased because the speed has increased. We know the starting speed is 0. Final speed is what we're trying to find. So we'll leave that as an unknown. Are there any other types of energy changing?
The bond energy.
Right,
from
the
fuel.
chemical bond energy of the fuel itself. And note that this is distinct from physical bond energy in the sense of changing phase. We're not really considering any phase changes here. We're just looking at chemical changes. So this is specifically the chemical bond energy of the fuel itself, or really of the reaction involving combustion of fuel and oxygen. And would you consider that an increase or decrease in chemical energy?
It has to be decreasing if we're looking at this as a closed system.
Yeah, everything else is increasing, so this is going to have to decrease to power it. And there's not really any, I guess you could say the indicator is the number of moles, how much of the substance there is. But we're going to have to deal with that more on a case-by-case basis. However, this one's actually not going to be considered a closed system because during the flight, what else is happening?
Oh, the weight is, you're losing mass.
Yes, but that mass doesn't just vanish. It just ends up on the ground.
Work is being done.
Yeah, we've got work happening, right? It says this toy rocket experiences an air resistance force of 100 newtons on average. That's a force applied to the object as it's traveling a distance, so that counts as work. And would you consider air resistance to be work entering the system or work leaving the system?
Leaving.
Yeah, the air resistance is acting against the motion. So we're going to have work leaving the system due to air resistance. So we've got the work of air resistance leaving. And it also mentions heat. It says we've got a total of 2,000 joules of heat lost to the surroundings. So we've got heat leaving the system also. Since we're losing heat, we'll write this as negative 2,000 joules. Also for air resistance, how do you usually calculate work?
Force times distance. So they gave you the force and the distance you travel. So you just multiply.
Exactly. Force was, what was that, 100 newtons? Yeah, 100 newtons force of air resistance, and it's traveling up 30 meters. However, since it's traveling upwards and the force is downwards, the force is acting against the distance traveled, we're going to call that a negative 100 newtons of force. Multiply those, we get negative 3,000 joules. So we know the amount of work, we know the amount of heat, so we get a total of 5,000 joules of energy leaving the system as work and heat. Any questions on that setup so far? So I think we should now be able to write out a conservation of energy equation. We've got these three changes. The change in total energy. Those all have to add up to not zero because this is not a closed system, but instead work plus heat. Fortunately, we know the values of work and heat, so we can just fill in those directly. And then we can fill in formulas for these. Potential energy of gravity is our usual mg delta y. Kinetic energy change is our usual 1/2 m delta speed squared. And what formula could we use for delta chemical energy?
You could use delta N, delta H.
Yeah, where n is the number of moles, because it tells us how many moles we've got, I think. Well, it tells us how many kilograms we've got. We can convert that to moles using the molar mass. Yeah, so we've got number of moles burned, number of moles consumed, times delta H per mole. Also, we've got to be careful about sign here. If we're consuming some number of moles of fuel, is the chemical energy increasing or decreasing?
Increasing? Increasing?
Is this chemical reaction taking in energy from other stuff, or is it giving energy to other stuff?
Oh, it's a combustion. Okay, so it would be decreasing.
Yeah,
Right.
If the chemical reaction is providing energy to something else, that means the chemicals themselves are losing energy. So we should treat this as negative. And that way we have a positive change for height, a positive change for speed. So we need a negative change for this, because I mean, these don't even cancel out. These have to add up to a pretty big negative. So this has to be an enormous negative to not only balance this out, but also still have some negative left over to account for the negative 5,000 joules of heat and work. Any questions on that so far? So some of these I think are going to be pretty straightforward. We know, for instance, that gravity is our usual 10 meters per second squared. What would delta y have to be? How much is the height changing?
30.
Yeah, that's positive 30 meters because we're going up 30 meters from 0 to 30. You could even write that as final minus initial, 30 minus 0. As for mass, what is the object we're talking about here? How much mass are we dealing with?
It's the rocket, but I don't know if you use the, well, it gives you net mass, I guess. So you can use that of 4 kilograms.
Yeah. So that's the mass of the rocket itself. But what is it carrying?
Oh, 2.4 kilograms of fuel.
Right. And also 0.64 kilograms of oxygen. However, it's burning half of that, and the exhaust products just end up at ground level at rest. So we really only need to consider the other half that it's still carrying. The half of it that it's not burning, we can basically treat as cargo. So that would be, I guess, 1.2 kilograms of fuel and 0.32 kilograms of oxygen. So we're going to have, we've got 4 kilograms of rocket. And half of the fuel is still on board. So that'll be 1.2 kilograms of fuel. And also half of the oxygen. So that would be 0.32 kilograms of oxygen. So that's what's still in the rocket when it reaches 30 meters. Add those together, we get 5.52. So we should really be treating the mass as 5.52 kilograms here. The rocket plus all the cargo is still carrying. The other half of the fuel and oxidizer, the other 1.2 kilograms of fuel and the other 0.32 kilograms of oxygen, they started off at ground level at rest, and they end up as exhaust and water at the ground at rest. So overall, they haven't actually changed their height and speed, and we can ignore those. Likewise here, this M is still going to be the 5.52 kilograms. The total mass of the rocket and the fuel and oxygen is still carrying. And then delta speed squared, how would we write that out?
You could just do V final squared since you start at rest.
Exactly. V final squared minus 0 squared is just V final squared. So that'll just be the unknown V final squared. Note that that's the only unknown we've got so far. And then carrying this into this, negative N consumed. That is the number of moles consumed. We know we're consuming half the fuel. That's 1.2 kilograms of fuel. But the formula is given more in terms of number of moles. We've got 700 joules per mole. So we're going to need to have number of moles. How would we convert number of kilograms into number of moles?
I think they gave you the molar mass.
Right. It says it's 120 grams per mole. And we've got 1.2 kilograms, which is 1,200 grams. So if 1 mole is 120 grams, how many moles is 1,200 grams?
Ten.
Yeah, should be 10 moles. So you've got 10 moles of fuel being burned, and also 10 moles still aboard, but that doesn't really matter, times 700 joules per mole. Note that moles and moles is going to cancel out. So we're left with joules of energy. And also a negative because we're talking about the chemicals losing energy and contributing that energy to other systems. And then we found earlier that work plus heat is negative 5,000. And at that point, it looks like V final is the only unknown left. So you can calculate V final, and that tells you the final speed at height 30. Any questions on that? All right, so try finishing off the algebra there, isolate V final to get some more practice, and feel free to email me if you have any other questions, and I will see you next time.
Thank you.
You're welcome.